Okay, 5.6 is going to be a little bit different. You know how we were finding the area under the curve and we found the exact area? This is kind of almost going backwards. We're trying to find an approximate of this, okay? So if we're trying to find an approximate, one way to go about finding an approximate is to make a bunch of rectangles that estimate the area underneath the curve. And it's really easy to find the area of each of the rectangles, isn't it? When would we use this? Because if we can just do the integral, why wouldn't we just do the integral and get the exact? Okay, sometimes there's going to be functions where you can't find the antiderivative. Okay, maybe it's like a function that you just have no idea how to do that. Then you could estimate it using these rectangles. Okay, the rectangles are actually kind of a huge part of calculus. So if you take a calculus class again, you're going to see the rectangles anyways. So. Okay, so you can't find the value for a definite integral unless you can find the antiderivative. So what happens if you don't know the antiderivative? You can approximate it using what's called Riemann sums. So Riemann sums just means we're finding a bunch of rectangles and finding the area of those. That was just a guy's name, okay? So Riemann sums, we're just going to use the midpoint rule, even though he had some other rules that worked as well to approximate it. So approximate the area under a curve by dividing the area into rectangles of equal width. So do you see how the width of these is the same for all of them? Okay. So we cut it into equal widths, and then if we're going from, well, let's use a different color. So if we're going from here to here, isn't the midpoint just halfway there? So you go to the midpoint of that width, and then you go up to the graph and you put a dot there. And then that's where you make your rectangle, okay? You do the same thing. If it's from here to here, you go to the midpoint, you go up to the graph, put a dot there, and then you draw your rectangle going right there. So does everyone see where these rectangles come from? Okay, go to the midpoint, go up to there, same thing with the last one, okay? And it'll tell you how many rectangles to use, so that's how you decide how many to cut it into. Okay, so to approximate this, let me get it so everyone can see it a little better here. So to approximate the integral from a to b, you'll divide the interval into n subintervals. So this one's divided into how many? 4. Okay, so your n is like how many rectangles you're doing. Okay, here's the width. You might want to highlight this. Some people find it easier to use the formula. Okay, so your change in x, you just do your b minus a and divide it by how many rectangles you're doing. Okay, and then what you're going to do with those, you're going to find the midpoint for each of the subintervals. So if the midpoints are these, x1, x2, dot, 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 x sub n, then to find the area of the rectangles, you would take what the width is times the height at that midpoint, right? And the height at that midpoint would be the y value at that midpoint. And to find the y value, you just plug it into the equation, right? So here's like a formula. It looks really messy. There's 2 different ways that you can do it. You can just do the change in x, which is your width, times the height, and then plus, and then do the same thing here, the change in width times the height, plus, and do it for all of them. Or the other thing you can do is just take the change in x and multiply it by all these added together. It's like factoring out the change in x, okay? So you get the exact same answer either way. So a lot of times it's going to, well, it's kind of written like this, but I probably wouldn't highlight that because you're not really going to use the limit piece there. But technically this is the definition of it here. Okay, now if I only cut this into, let's say, 1 rectangle. If I only cut this into 1 rectangle, the midpoint would be halfway between those, right? And I would go up to the graph halfway between, and then I would draw a rectangle. Do you think 1 rectangle is more accurate, or do you think 4 is more accurate? 4, right? What if I did 100? That's going to be more accurate. What if I did 1,000,000? It's going to be almost exact, right? The more you do, the more accurate it's going to be. What this integral does is it actually is like taking it and making it into like an infinite number of rectangles. That's how it's getting that exact, okay? So the larger value of n, the closer it's going to be to the actual value, okay? Okay, so we're gonna use this example here. You guys have the picture, right, on your paper there. So use 4 rectangles to approximate the area of the region bounded by the graph. So this is my equation, my y equals x squared plus 1. The x-axis, which is obviously down here, and then x equals 0 and x equals 2. So before, we used to go, okay, x is 0 is here, x equals 2 is out here, and we would just shade that entire thing, right? But what are we doing now? We're doing 4 rectangles, right? So we have to divide this into 4 rectangles. So what's the width of each of these rectangles going to be? A half, right? I would go from here to here, and then I would go from here to here, here to here, and then here to here. So that's going to give me my 4 rectangles. And then what do I have to do with those rectangles? Find the midpoints. So let's put the midpoints in a different color here. So my midpoint would be where for this rectangle? 0.25. So you would go at 0.25, and then the midpoint here would be 0.75, and 1.25, and 1.75. And then what I think I typically do anyways is I just take and do like a dotted line that goes up to there. So you do that for each of these midpoints. Okay, because this isn't actually part of my rectangle, it's just showing me where my rectangle is going to go. And then once you have that, you're going to do what? Draw your rectangle. So this rectangle is going to have this height going across there, and then it would go down to here. Okay, the next rectangle would hit here where that dotted line hits. And then it would go down on both sides there. Okay, the next one's going to go here. Oops, that one needs to be a little bit higher, so I'll adjust that in a second. So do we have any questions on that? So you guys can sketch those in there. And the reason we typically use those, midpoints is because when I'm finding the area of this rectangle, do you see how I'm getting a little bit extra on this side, but I'm getting a little bit less on this side? So it gives me a decent approximation, right? And it's not going to be exact, but it's actually kind of, close to what it needs to be. So, any questions on that? Okay, so let's see how accurate this is. So we're good there. I'm going to get rid of that. It's a little trippy. Okay, so let's go ahead and try to actually come up with what our area is. So I'm using obviously 4 rectangles, so my n equals 4, right? And we said I'm going to write what my midpoints are here quick. So they were at 0.25, 0.75, 1.25, 1.75. So those are a couple important things to get noted there. So how do I find the change in x? What was that formula? B minus a over n. And your b and your a are what? 2 and 0, right? This is your a to b. So our b minus a is going to be 2 minus 0, right? Over n, which is 4. So my change in x is 1/2. That just tells me the width of my rectangle. So does it make sense that I'm getting a half there? Yeah. So I'm going to denote this. I'm using midpoints, and I'm doing 4 midpoints, okay? So that's why I'm writing M4. And then my half is going to get multiplied by what my height is, right? So what my height is at 0.25. So wouldn't that be my f at 0.25? Everyone see what I'm doing there? Okay, you can actually plug it in. I just write it this way first, and then I'll actually find the values. Okay, the next one, I'm going to take a half, and I'm timesing by my f at what value? 0.75. And then the next one would be a half times f of 1.25 and 1.75. And then how do I find my function at 0.25? Plug 0.25 in. An easy way to do this, if you have your calculator, put this equation into your y equals. Okay, so throw that equation in your y equals. Okay, so if you go to your y equals, you just put the equation in. And if you don't have it, obviously you can use mental math there. But we've got x squared plus 1. Now if I go to my table, what's the first value I care about? So go to your second table set and go to 0.25. And what are my increments that I'm going up by for the values that matter? 0.5, right? If not, you'll just have to search for them, but it just seems silly to search for them when you can just pick out the ones that you want here. So really, the only values in this table that matter are the first ones there, right? So I can even just kind of zoom in on these guys here, and these are the only ones I really care about. Okay, so questions on how I got those values? And then you just put those values into what we have started here. So let's go ahead and finish that. So I've got my half out front. And then inside here, f of 0.25 is 1.0625. F of 0.75, put that one down. So any questions on what I'm doing here? And then you can just add those pieces up, right? So go ahead and throw those in. What do we get?
I got a total at the end. 9.25.
Did you do a half?
4.625.
4.625, perfect. Other people getting that? Okay. I'll show you this here in a minute. Does anyone have questions on this one? So if you go to that website, it's up here also. It's also on your, or I was on the smartboard there before. We get this page here. Is that where everyone's at? Okay. Now what we want to do is we want to graph the Riemann sum, and we're going to just put our equation in there, which our equation was x squared plus 1, right? So we're going to go x, and then that caret button is above the 6, right? So x squared and then plus 1. As x goes from what to what? 0 to 2. And then how many rectangles did we use? 4. And we're using midpoints. That's going to stay the same here. Now here it says print estimated and actual areas. So the estimated area is what your Riemann sum gives you here, okay? The actual area is if you actually took the integral of it and found it that way. If you want to, you can change the color, you know, that doesn't really matter there. All right, so you can do those things. It's not going to change this, okay? One of the questions, I want to say it's like 20-something in your homework, they tell you to use like a program. This is the program that you would use for that question. Okay, you can check your answers using this. Obviously, you wouldn't have this for like a quiz or a test, right? So does everyone understand how this works? I'm not sure. I think some of them are graphed for you. Okay, if I had to do like a square root of a function, what would I do in here? Any ideas? To the half. So like let's say I'm just making something up here, x plus 1 and it's the square root of that. Whoops. I would just do x plus 1 and then raise it to the 0.5 power. Okay, that would give me like the square root of that. Okay, and then obviously you can switch the number of rectangles you're using and things like that. Okay, so does everyone see how this works? Yours isn't working? I'll check it here. Okay, so did we get the same answer with that x squared thing? With this x squared plus 1, with our 4 rectangles, did we get the same estimated area as what we got in class? 4.625? Yeah. Okay, so it's just a way to check your answer there. Okay? So any questions on that? Okay, let's go to the last page here. Okay, so the last one here says use Riemann sums with n equals 4 to approximate the area of the region bounded by the graph of f equals 1 over x squared plus 2, the x-axis, and going from -2 to 2. It's kind of helpful to obviously get those, get a picture of that, but you don't even need a picture of it. Okay, so let's not do this in our calculator and let's just do it out by hand. Then we can test it in that Wolfram if we want to test it there. Okay, so if I'm going from -2 to 2, typically what I do is I draw a little number line here. And how many spaces or how many spots am I doing for this? 4, right? So I'm starting at -2, then I have one rectangle go there, one would go here, one would go here, one would go there. And I'm going from -2 out to 2. And then I just kind of fill in the number line. So between -2 and 2 is what number here? 0. And then here would be 1, and then here would be -1, okay? So this breaks it up into the rectangles. I'm not actually drawing the graph here. I'm just coming up with my midpoints. So where would my midpoints be located? It'd be at like the halves, right? Here, 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 and here would be my midpoints. So let's go ahead and write our midpoints. Because if you don't get your midpoints right, there's no way to get the questions right. So midpoints would be -1.5, -0.5, +0.5, and 1.5. And the other thing I need is my change in x, right? So to do change in x, we do b minus a over n. And my b is 2 minus my a is -2 over 4. So I end up with a width of 1. And does that make sense that this width is 1 here? Yeah, okay. I always do this and then I double check to make sure it makes sense up there, okay? So when I'm trying to do my midpoint with 4 pieces here, what number goes out front of the whole thing? Just that 1, right? The width is 1. And then inside here, my first y value I'm looking for is at -1.5. The next one is at -0.5. And then it's at 0.5. And then at 1.5. Okay, then you can use your calculator to come up with those. So go ahead and put that in your y equals. So just put that into your f of x, 1 over x squared plus 2. My table set, where would I want to start this time? -1.5, and my increments were 1. And then look at your table. Now the thing with the table is, do you see how there's only like 5 decimals here? Sometimes, I mean, for our sake, it's probably fine. If you felt like you needed more decimals, how could I find what these other decimals are that are past that? If you just scroll over the top of it. So then you end up with this, you know, humongous decimal there. Okay, so if you feel like you need more decimal spots, especially when we get to like AP Calc, we'll actually round them out a lot further. I would say for now we're probably okay just sticking with those, okay? And then you just do 1 times each of those y values. So go ahead and figure out what you get there. And then you can double check it on that website if you want to check it there. Okay, so these are the values that we care about there. So if I throw this into the website, I'm going from -2 to 2. Using our 4 midpoint, so that all seems like it works. Did we get like 1.35948? Okay, so that's what we should have. So, questions on that at all? Okay. If you want to look at the next one here, does your paper say e to the x squared? Yeah. Okay. So go ahead and see if you can come up with how to at least get that one started, okay? We'll talk about it in a few minutes. Okay, so we're trying to approximate this integral here. This is one of those cases we can't do the antiderivative of what's in here, so we kind of are stuck using an approximate instead of the actual. So I'm going from 0 to 1, and I'm cutting it into 5 subintervals, so I've got these 5 gaps here. So if I'm cutting it into 5 pieces, what would this first piece be? 0.2 or 1/5, right? So either way is fine. So this one is 0.4, 0.6, 0.8. So where are my midpoints? Yeah, all the odd ones here, right? 0.1, 0.3, and so on. So that's the first thing you want to identify. The other thing we need is our change of x. So b minus a would be 1 minus 0 over n, which is 5. So I just get a 1/5 or 0.2, whichever way you want to do that, okay? So when I'm trying to find my midpoints with 5 subintervals, what goes up front? 1/5 or 0.2, whichever way. And then I'm finding my function at 0.1, and then at 0.3, and so on here. So I'll write these out. Do we have any questions so far? Okay, now let's say we don't have our calculator to do our table. Just for the start of this, obviously we're going to need it. I just want to make sure you can do it in case you don't have your calculator. All this is saying is we're plugging 0.1 into this function, right? So wouldn't that value just be e to the 0.1 squared? So isn't this a number here? So if you don't have your calculator, you could write that. This one would be e to the 0.3 squared, and so on, right? You can use your calculator now if you want to come up with what those values are. And then if you want to check it at that Wolfram, we'll see. I'm not sure how e goes into there, if that works. It doesn't work? So I guess you'll have to go with, we'll have to just check it with each other here then if we can't use the e in there. Okay, so I'll give you a minute to finish that one. I suppose if you try this in the Wolfram, obviously it's having some issues with the e thing because it's, you know, reading it as a letter instead of a number. Couldn't you just do the decimal approximation if you wanted to see if your answer's about right? So if you just do e to the first in your calculator, you get 2.7182812828. Okay. So this should give us a pretty good idea if we're right or not. So we get about 1.454. Okay. So if you need to, that's kind of a way around the e thing to check your answer. Okay. You're not going to have this again for a quiz or test, so it's definitely not something you want to jump to right away. But okay. So that would be your answer for here. Any questions? That was 1.454. 1.454 is what I have. Well, this here, yeah, these numbers are where they come from. So if you have that near y equals, you can use your table again. So questions on that? There we go. Okay, then your homework. There's not a whole lot of problems there, okay? But they take a little bit of time. Just be careful that you pull your midpoints right, is the easiest thing to mess up on. So